Welcome to Femap version 12. I'm going to go over some new features, some old features, some new solver features, and we'll just build a little test model here about kind of heel and toe loads you can get on bolts where actually, a little prying action will increase your bolt load. So let's go ahead, and I'm just going to start off. Let's make a little angle clip, and we'll model it to get the kind of investigate this effect. So here's a block I made. Use the hollow command. Just knock off these sides. We'll go 1/4 inch. And we'll also put a fillet in there for 1/4 inch. Now we need a little more meat here, so let's do some feature editing. Surfaces, and we want to what we'll do is offset these surfaces by 1/4 inch at a time. And let's just make this part a little bigger. That looks pretty good. Give me something to put a hole in down there. Do one more. All right, we'll put our hole in right in the middle of this face. So I'll move my work plane to that face. Then I'll move the center of the work plane to the CG of that surface. So now when I put in another primitive, I'm going to do remove cylinder of radius of 125. So there's my hole in the bottom. So let's get this ready for some hex meshing. We need to slice them up. So we'll slice plane I want here, YZ. And move the snap mode to point. So we'll slice him there. Previous command with the right click. And this plane is XZ. All right. And I want to force a map mesh on here too. So I'll say mesh control, approach on surface. We'll get the two ends and say mapped. So now when Femap sizes this for hex meshing, it knows I want to map mesh on those. I'm going to say size on solid. Pick my 3 solids, say hex meshing. Let's go for exactly 125. You'll see now there's more nodes here than there are here for the map mesh. Let's go ahead and hex mesh this, say geometry, hex mesh solids. And I need to pick a material. We'll just make this out of aluminum and say okay. So now we get a pretty nice hex mesh going here. Now a new feature in version 12 is we have the pads and washers for surface meshing. We also added them in for solid meshing. So I can go in here to geometry editing. I'm going to go into pad. And I'm going to say add the washer and do it if it's a solid. So when I pick that hole now, it actually went in there, and if I turn off the mesh, you'll see it kind of split up the geometry and set everything up and kept the hex mesh rolling. So now we got a real nice area there for hex meshing. So this heel and toe, what happens is when you pull up on a fitting or something, it's going to kind of fulcrum from this edge over here and increase the bolt load. So let's go ahead and investigate that. So first thing we'll do is we need to constrain this. Let me turn off my thing there. I need to constrain it. And I'll just say, let me simulate a bolt head holding this thing down. So this will be pretty simple constraint. So we'll say on surface. We'll go pick those 4 and just say pin this thing down. We could get into bolt preloads and stuff, but perhaps we'll look at that later. And we'll just pull up at the top here. So I need a load. So I'll say new load set. We'll go vertical load. And let's create a new one on surface. Pick that top, and we want 5,000 pounds in the Y. Now let's just do a simple linear static run. Let's say without this the heel and toe effect that we're going to model. So what I'm going to do right now is let's just save this. And I've been saving these in a, because we'll run solution 401 in a minute. So we'll do heel toe 2. All right, he saved. But let's just run a static analysis without the heel toe effect. So I'll say new, and we'll create a just Nastran regular static run. And the only thing I do want to get out of here, I want to make sure I get my force balance so I can do a nice free body here in a minute. So let's go ahead and just say analyze. Nastran's going to go off and run It's done already. The analysis finished. So let's just take a look at what we got here. So we got one result set, and you can see that the part actually goes below here. So that's kind of the physics we're going to simulate in a second here to stop that from going down. But let's look at the reaction force. So in Femap, we have this free body diagram we can do. So let me get the post toolbox up. And I'm going to say free body, create a new free body. And what I want to do is I want to put in the elements will be all the solids, which is the whole model right now. And what I want to do is an interface load across the nodes on this face. So let's go get those same nodes we constrained. And we'll put a thing in the middle there. So let me turn off the individual free body. Oh, wrong button there. So we got the summation forces, the individual. So we got a total force there, and let's turn off the moments on the summation. So you can see that the bolt load 5,000 exactly matches the applied load. So we do have a free body here, and that's the 5,000. Well, let's go take a look at what can happen if you actually take that heel and toe into account. So let's turn that off for now. We can even turn off the free body. We have C-bush to ground elements, which will basically allow me to put a one-way stiffness, and I can hook that to a function. So what I'm going to do is I'm going to create a function. Create a function here. Let's just go in our function. We'll say new, and we'll do displacement versus force. So we'll be able to attach this to a C-bush stiffness one direction. So what we're going to do is we're below zero displacement. So, you know, from way low to 0.00 until it just starts displacement. So yeah, minus 10. I think this should be 0. So no stiffness. Right at 0, no stiffness. But as soon as the displacement starts going up at all, let's just do, you know, I'll do 1 e to the minus 6. I want it to get stiff. And you basically kick in kind of a one-way constraint. And then that's a ramp function. Let's just also put that down at 10 as well. So basically, as soon as displacement starts going positive, the stiffness is going to go on. All right, so we got the function, and I want to do that in a certain degree of freedom. So let's make a coordinate system that's pointing. I want one of the vectors pointing here, probably x. So let's do model coordinate system. And what I'm going to do is just create one align with my bottom down here. We'll say just xy locate. I'm going to create the centroid of the coordinate system here, the x-axis here, and the y-axis this direction. And there's my coordinate system. I really want x pointing down, so let's just spin them around. Modify, rotate by coordinate system. And what I want to do is rotate just 90 degrees about here. And that'll put my x pointing down. Now we need a property for our C-bush to ground. So let's create a new spring damper to ground, C-bush. And what I'm going to do is have a stiffness of 1 here. That'll kick in and connect that to that function. So it'll use that as my stiffness in that one direction only. And I want it oriented to that coordinate system. So as soon as it goes positive x in coordinate system 3, stiffness will start kicking in. So we need to make a bunch of C-bush to ground elements here. Now we could probably just do them one at a time, but I wrote, in order to do this a little quicker, I wrote an API that just generates them for me. So I'm going to run this API, pick that property, and pick all the nodes. Actually, we'll do it by faces. So pick one face I like. We'll find the rest on the bottom there. And this will create all those elements for me. That's what the API is great at, is automating some mundane task. So right now, this would be a one-way CBlush. So to run this, to kind of get it to run and go real nonlinear, let's go run this in solution 401, which is something new in Femap version 12. So let's say model analysis. I'm going to create a new, and this is solution 401, multi-step structural. And in 401, let's go here, look at the control options. We'll just take the defaults. Now what I found is to get this to converge, you basically have a real small first time. Let's do 25 increments here, and let's get those initial convergence going. We'll put out results at everything, and then we'll let it finish with another 20 steps all the way up to full load. And the other thing I want to do is, all this should be good. Same thing as before. I want to make sure we get the force balance so I can look at the free body diagram. Let me just save this where we're at. And let's go run that one we just created. So we'll say analyze. And we should start to see some nonlinear convergence. So it's working on that first very small time step. It got that going. As long as this keeps going up, it's a pretty good idea. We got convergence. That looks good. So let's go look at those results. So now we got, those are all the results. Let's go look at just that multi-step, and I'm going to say animate this study. And you'll see it kind of, I had that first small time step to allow stuff to get kind of connected and going. What you can now see, I'm going to turn off my geometry. And let's turn off all those one-way elements. So elements by type. Well, you'll see that it never goes below 0 here. So we're kind of getting that heel and toe effect. And just for fun, let's turn on the stresses. Yeah, looks good. Okay, and the big thing would be, let's go look at that free body again. So let's go all the way down to the last result set. Turn it on. We'll turn off the stresses, don't need to see them right now. And let's go back and turn on that one free body. And we'll see that, actually I'm going to wireframe here for a second. You'll see now that the total load being reacted is 11,413. So that, kind of that fulcrum there multiplied our load by a significant amount. So we actually got a much higher bolt load than our 5,000 pounds. So that certainly is true. And let's go back to the free body elements. And I want to see the nodal vectors. And you can actually see there's the reaction forces at the constraints, but you can also see the reaction forces now from the one-way constraints. You can see how it, right in the middle, closest we get the highest load. Out to the edge, we're picking up some load, picking up some decent amount of load out here at the sides. So that's kind of what's contributing to that heel and toe, and putting that couple in there that's making that much higher bolt load. And so that's solution 401. You can see the nonlinear stuff here. We showed some hex meshing, some free bodies. This is Femap version 12.